Thank you very much for the introduction. What I have the pleasure to talk to you about today is basically the dengue and the sequencing of an antibody repertoire. I'd like to make you aware of what's happening there as an immune response to dengue. And then we are going to discuss some artificial intelligence methods applied in order to predict these antibody repertoires and the repertoire level or at the sequence level that are specific binding the dengue virus. Now, dengue virus is a global threat. It's endemic in several countries and can be life-threatening. There's currently no treatments for dengue, and there's only one licensed vaccine. However, it's basically advised to be used only in certain cases of dengue. So we still have 5 different variants of dengue and no cure there. Therefore, broadly neutralizing antibodies, or antibodies as you see here that could specifically bind to dengue and prevent it from infecting other cells, then are very important in this realm. What we can do in order to basically understand better these broadly neutralizing antibodies is to study the immune repertoire, the immune response. Antibodies are secreted by B cells that are current cells in our body. The diversity of this antibody repertoire, so the diversity of the collection of all different antibodies that an immune response, an individual can produce, is coming because of this VDJ recombination. So 3 different genes, 3 different gene families are recombined, further mutation as are introduced into the antibody, and we have a very high variability of antibodies. The antibody space, so the space of all potential antibodies, can be up to 10 to the 140 power. So that is more than stars in the universe. Basically, it's a huge diversity of the theoretical space of antibodies. And each individuals can produce up to 10 to 12 antibodies, so 1 billion antibodies. And each of these antibodies is different in its sequence. So if we represent the antibody as a genetic sequence, we take the sequence of the amino acid, so the protein sequence of each antibody. That's a huge diversity. Now, the 3 questions that we posed are there any dengue-specific signatures that we can actually retrieve in the sequence? And that was the first question at the repertoire level. So can we say from the sequence level which antibodies are coming from a dengue-challenged individual or from a healthy individual? There, the second question was if there are any broadly neutralizing antibody signatures at the sequence. So what we wanted to find out is, can we predict if, only from the sequence, if an antibody can broadly neutralize dengue, which means can broadly, can bind to all 5 different serotypes of dengue and neutralize it, prevent it from infecting other cells. And the third question is, can we actually engineer de novo dengue specific sequences in order to basically design better therapeutics, so to provide therapeutics that would be new antibodies, or also to guide a little bit vaccine design. Which antibodies should a vaccine elicit from an immune response that would specifically bind to dengue? So in order to answer these questions, of course, we needed to start from data. And the data that we have collected was from 137 samples of dengue and healthy individuals, and these data represented more than 2 million sequences. Some of the data was publicly available. The publications are listed here for your reference. And the first step, of course, we heard also before, was the pre-processing of this data. So we went on into taking only those sequences that are productive, so that would give a functional antibody, that are longer than 4 amino acid, and that are basically appearing more than once in the data set in order to clean the data or to filter out all the spurious error sequencing sequences and so on. After we have basically collected all of these samples from background, which for us is a patient or an individual that was not dengue challenged, and dengue data. So these are all of the sequences. Then we have applied machine learning methods in order to answer those first three questions. So can we detect signatures at the repertoire level? Can we detect broadly neutralizing antibody signatures at the sequence level? And can we predict or engineer novel antibodies that would broadly neutralize dengue? The first thing to do was actually the raw data. We did some pre-processing. We had the clean data as discussed in the previous slide. So only CDR3, so only a portion of the antibody that was functional, that was longer, cleaned the data for errors and so on. Then we have also encoded the data in order to actually use it as an input in order to detect features in all of the different machine learning models. We have trained these models, and then we have evaluated as well the models for the results given. But this is the general pipeline that we have followed. In specific, we have used basically some specifically classification machine learning models. We have used the multi-layer perceptron, RNN, and long short-term memory neural networks as supervised neural networks. And then we have also used decision tree learning in order to benchmark these different machine learning methods. As we mentioned, the first step, and maybe the most important here, is to actually encode the data correctly, so to encode the sequences correctly, in order to understand also what kind of impact different encoding methods would give to our data. We have used 5 different encodings. One was the one-hot encoding, in which the presence or absence of an amino acid at one specific position in the sequence is given a 0 or 1. Then we have encoded with an integer encoding, so assigning from 0 to 22 to each of the amino acids of the sequence. Then we have also encoded the k-mers, so trigrams of the sequence. We have used BLOSUM K encoding. BLOSUM K is one method in which you basically encode based on the similarity of the amino acid properties of the sequence using a distance matrix. I will not go further into details, but this is a very known encoding technique in the protein space. And then we have also tried to set up some physiochemical rules from the beginning in order to encode the different sequences based on the specific properties that each amino acid in the sequence had. And we have come up with 93 rules of actually encoding sequences based on their properties, for example, hydrophobic sequences and so on. The first result is basically to benchmark the different encodings, and what we have used for that was the very simple neural network, and we have tried to input sequences, encode them, and then also benchmark all of these methods on what kind of performances they have output. And one-hot encoding looks like it actually determined the higher prediction accuracy. So we have here all of the rules combined from us, and with the arrow, the empty arrow in red, and the red arrow will show you the performance accuracy of the one-hot encoding. So basically, we came to the point that with all the encoding techniques that we have benchmarked, one-hot encoding would have been the encoding that we would have used through the machine learning classification with other methods. So the first result was basically that neural networks can predict very accurately all of the antibody repertoires. As you see here, all the prediction accuracies are close to 1 or 90% accuracy, in which all of the dengue phases, so acute dengue, post-convalescent dengue, or healthy, can be predicted with a very high accuracy. Here is indicated the whole pipeline. So from the sequencing platform that was used, you can use different sequencing platform, to the IG-BLAST, annotation of the sequences, the pre-processing, and then the encoding of the sequences through the k-mers, trimers in specific, and the functions that were used. So the ReLU function and the softmax for the neural network. So the first result was very promising. We can predict at a very high accuracy, prediction accuracy, the repertoire, so the collection of all the antibody sequences, if they are coming from a dengue or not dengue challenged individuals. And moreover, we can predict also the specific dengue phase. There was, as you see here, basically one accuracy that is 50%, that is chance, that is the post-convalescent dengue. So after individuals have recovered from dengue, it's very hard to tell if these, if the immune system, so if the collection of antibodies are coming from a healthy or a post-convalescent dengue, and that makes complete sense clinically. So it was also one of the results that also made us more confident in actually doing things rightly. The accuracy for the other classes is the acute dengue was predicted with 97% accuracy, convalescent dengue 80% accuracy, and non-dengue or healthy individuals were also predicted by 100% prediction accuracy. The next result is the investigation of the parameters. So we tried basically with different models, we tried with different layers of the neural networks, we tried to fine-tune a little bit what kind of parameters, what was the best parameter for a machine learning model to predict dengue repertoires at the sequence level. And we came to the result, I will not go into details into this slide, just to show you that we actually also investigated the parameter space. We came to the result that one of the best models with a 96 validation accuracy was basically the long short term memory, the neural networks. And this was a result that actually all of the neural networks, as you can see here on the top right, are predicting dengue with very high accuracy, specifically the RNN. So mainly the multi-layer perceptron is the highest accuracy one. So the simple networks also will predict with 80 or more percent accuracy network, prediction accuracy. The next kind of interesting result was that through all the 137 repertoires that were classified, 118 of these dengue challenge repertoires were classified correctly, and only some of the repertoires of the non-dengue challenged ones were classified incorrectly. However, we went in detail into actually learning why this misclassification happens. And yeah, this is an overview of all the results of the models used. So basically, you will see that the highest sensitivity was from the multi-layer perceptron. The highest accuracy was given from the long short-term memory networks and with high specificity as well. Random forests also did well, between 92 accuracy, 95 sensitivity, and 90 specificity. However, the simple neural networks did actually better. And from these ones, of course, duration in time was the shortest with also multi-layer perceptron, while the long short-term memory neural network did require more computational time into giving the result. So we also repeated the experiment using support vectors. We wanted also to see if we could add the sequence. So now we know that we can tell repertoires specifically if they're coming from a dengue challenged or a healthy individuals, the entire collection of the antibody sequences. We wanted to know if at each sequence we can predict if one of these individuals had developed naturally broadly neutralizing antibodies. And in order to do this, we had also basically built a database with 28. That's very little, but however relevant basically number of sequences. So we built this database in order to see if the repertoire, so if the repertoire can have signatures of broadly neutralizing antibodies. And while even support vector machines can classify with 89% accuracy, so the lowest accuracy of all our machine learning benchmark methods, it cannot actually tell if these individuals have or don't have a broadly neutralizing antibody sequence in their repertoire. In our method, then, we wanted to understand how the sequence was assigned. So while we classify a repertoire, if it's dengue or not dengue challenge, so how did the machine learning assign the class to this repertoire? And we noticed that all the misclassified repertoire, so for example, if a repertoire was dengue and was misclassified as background, had a lot of sequences in their network that were very similar to sequences in the background or healthy repertoires. And this was the base, maybe, that the machine learning also encoding the sequences gave the result to. So in order to basically validate our finding, we went on into seeing how the repertoires were classified. And you see here in blue the dengue challenged repertoire and the dengue specific sequences. And on the top bar, you will see the predicted repertoire. On the bottom bar, you will see the actual repertoire. And in blue are the dengue sequences, and in ochre here are the non-dengue sequences. So basically, if the actual repertoire was non-dengue and it had a very little amount of non-dengue sequences, then the whole repertoire was classified as non-dengue. However, if the repertoire did have a few dengue sequences and it was a dengue challenged repertoire, however, it had also many sequences similar to the background repertoire, it was misclassified as non-dengue. So the few misclassifications happened because of this reason. And what we thought of doing is to actually take this to our advantage, and we designed some novel sequences very similar to broadly neutralizing antibodies in dengue. So basically, we introduced mutations in the sequence by sequence alignment, and then we mapped these newly developed, newly engineered, newly designed sequences to the dengue challenged repertoire, and we found similar sequences to them. And in order to validate the approach, we found out that basically all of the sequences that are in the dengue challenged repertoires can be mapped through CDR3 length and through similarity as broadly neutralizing sequences. So basically, by using neural networks, we could classify exactly the sequences that were in the dengue challenged repertoires as broadly neutralizing sequences. By using the similarity. So here I come to the conclusions of what we had performed in this work. One is that we can actually use deep sequencing in order to find dengue antibody signatures at the repertoire and at the sequence level. So we do need this technology in order to, and this technology can be used in order to detect these signatures. Second is that the machine learning methods actually can detect and can predict with high accuracy the entire repertoire at the sequence level. And one of the best machine learning models, best performing machine learning models, was this long short-term memory neural networks that could actually tell with the highest accuracy if a repertoire was coming from a dengue challenged individual or from a healthy individual. And we hope that we can see also the potential that these machine learning methods can have in order to predict in individuals that do have broadly neutralizing antibodies, to predict these broadly neutralizing antibodies at the sequence level, and then propose these as new therapeutics for the dengue individuals and for the dengue endemic in the world. So with this, I'd like to conclude my talk, and I'm open to questions. Yes, not without thanking actually who has mainly done this work. So my group, AI Health Lab at the Fachhochschule Nordwestschweiz, and Wellcome Trust for very generously funding the work, and of course AINet and the ETH spin-off community, and the 5 cantons that also support the lab. And thank you all for your attention. Are there any questions?
Thank you very much, Enkelejda, for sharing your work and the work of your group. So one question that we have is that initially you showed that the data that you got an access to, some of that was kind of publicly available, and also came from different parts of the world, like there were different regions. So does that variation in kind of underlying population genetics kind of influence the work that you're doing at identifying those signatures?
That's a very good question, actually. It's very difficult to answer this question because the field at the moment is actually still understanding the genetic variation of different populations on the immune system. So there are different works that just came out, and one work that we also published a couple of years ago, that basically the genetic determinant is very high. However, the stochasticity, the randomness introduced by these mutations and by the recombination, somatic recombination of different genes at each antibody sequence does allow to think, to think that actually this randomness prevails on the genetic component. However, the field is also checking now on the personalized level of genes that you have. So basically the recombination will happen at your personalized level. So there is also this kind of work ongoing. However, very good question. The field is still ongoing to clarifying the genetic influences to the actual immune response. So I think the influence is there. However, it's a bit further from what we can, from a definite answer, even in the immunology books at the moment.
Absolutely, yeah. Makes sense. Another question is more on from a model complexity, and especially more on the translating the models to helping with, let's say, managing those patients or helping with clinical practice. So the question is that if you were to take one model into the practice, would you take a more complex but accurate model, so LSTM, over a simpler and less accurate model, the MLP? What would be your preference?
That's actually, I can answer with what we are doing in the clinical practice with another project. So we are trying to actually do clinical decision support system for autoimmune diseases. This can, of course, be translated into the immune work as well. And what we do is we provide the clinician with different models, and we actually have them run on the back end in order to give a wider flexibility and try also to educate as they use the model. So we try to provide a benchmarking on the tool. So I wouldn't select for one of the best performing models to integrate in the tool, also because this might change with the data and with the upcoming data. So when you actually redynamically calculate things with more data or with different kinds of data. So I would provide the clinicians with the different models, and I would also educate them at the same time. So I'd maybe start from reshaping the medical education at the university level, what is already being done here in Switzerland, with a bit more informatics and data science and machine learning insights. Yeah. So I would provide the clinical decision system with all of the machine learning models or one type in order to allow the clinician to benchmark them as well.